Hello again, guys, and welcome to the second part of the lecture on Math 23 entitled Absolute Extrema and Lagrange Multipliers. In the first video, we learned about the absolute extrema of functions of more than one variable and how to compute them. In the second part of the lecture, we will talk about a method of finding the extreme values of a function given a particular constraint, called the method of Lagrange multiplier. This method finds many applications in real-world problems, especially in optimization. So shall we begin? Suppose you have a surface given by the equation z equals a function of x and y, and we want to find the maximum value and the minimum value of z such that the variables x and y follows a certain condition or constraint given by g of xy equals a constant k. You can think of z as the revenue function which you want to maximize given limited resources when your resources x and y follows a certain condition given by g of xy equals k. Another way to look at it is in reference to the example we had in the previous video. If you recall, in the previous video, we solved for the extreme values of a function over a triangular region. It just so happened that the region we are given in that particular example are composed of line segments which are easy to manipulate algebraically. However, not all boundary curves are like that. Some boundary curves are expressed in a complicated equation given by g of xy equals a constant. In that case, it is not easy to express the function f in terms of only one variable. This method that we will be talking about today can also be used to find the extreme values of a function over a boundary curve. The function z equals f of xy is the function that we want to maximize or minimize is called the objective function, and the function g of xy equals k is constraint. Now consider this objective function z equals f of xy and the constraint g of xy equals a constant k. So suppose we want to find the maximum value and the minimum value of z over all points satisfying the constraint. In other words, we collect all points on the surface z equals f of xy whose projection on the xy plane is the constraint g of xy equals k. Clearly, the minimum value is attained somewhere in this point, and the maximum value is attained somewhere at this point. But how do we actually find them? Notice that for every particular value of z, we get a level curve on the surface. That is, if z equals 1, we get a level curve somewhere here, and if z equals 2, you get another level curve somewhere higher, and so on. Now let us put those level curves on the xy plane together with the constraint function. So this black circle here is our constraint function g of xy equals k, and each blue circle is a level curve of the surface. That is, this is the level curve when z equals 1, this is the level curve when z equals 2, and so on. Finding the highest value of z over this constraint means that finding the highest level curve that barely touches this black curve. Translating that on the two-dimensional plane, that means finding the highest z such that the level curve barely touches the constraint function. And note that that happens when the constraint function is tangent to that particular level curve. Likewise, the minimum is achieved when the level curve is tangent to the constraint function. At these points of tangencies, the normal line to the level curve is parallel to the normal line of the constraint function. Therefore, intuitively, we say that the relative extremum value of a function f of xy subject to the constraint g of xy equals a constant happens when the normal line to the level curve of f is parallel to the normal line to the graph of the constraint function. So if the normal lines are parallel, We can also say that the gradient vector to a level curve of f is parallel to the gradient vector of the constraint function at that particular point. Now we state this observation in a theorem. So suppose the functions f and g are functions of two variables x and y with continuous first-order partial derivatives. If f has a relative extremum at the point x0, y0, subject to the constraint g of xy equals a constant k, and the gradient of g at the point x0, y0 is not the zero vector, then there exists a constant lambda such that the gradient of f at x0, y0 is equal to lambda times the gradient of g at x0, y0. This is just the mathematical way of saying that the gradient vector of f at that particular point is parallel or a scalar multiple of the gradient vector of g at that particular point. Simply put, the relative extremum of f happens at the point where the gradient of f is parallel to the gradient of the constraint function g. So to find the relative extremum of f, we just solve for the point x0, y0, where the gradient of f at that point x0, y0 is equal to some constant times the gradient of g at that same point x0, y0. Before we proceed in doing some examples, of course, we will have to prove this theorem. First, let us consider the case where the gradient of f at that point x0, y0 is the zero vector. We want to show that the gradient of f is equal to a particular constant times the gradient of g at x0, y0. But this is satisfied trivially because we can just take lambda to be 0. Next, we take the case where the gradient of f at x0, y0 is not the zero vector. We want to show that the gradient of g at x0, y0 is parallel to the gradient of f at x0, y0, assuming that f attains an extremum at x0, y0. To do that, we represent the curve defined by the constraint function g of xy equals k by a vector function r of t equals x of t, y of t, such that r prime of t is not the zero vector. Notice that the equation g of xy equals k only involves the variables x and y, and its graph lies on the xy plane, so the vector function r of t only has two components. You can think of the third component, z component, as 0. Let r of t naught be x naught, y naught. This means that the point x naught, y naught is generated when the parameter t equals t naught. And in the function f, let us replace x by x of t and y by y of t, such that f is now a function of only one variable t, and we write it as phi of t. Since f has a relative extremum at x naught, y naught, meaning x naught, y naught is a critical point of f, then the derivative of f at x naught, y naught should be equal to 0. Or the derivative of phi at t naught is equal to 0, since t naught is the parameter t that generates the point x naught, y naught. Again, phi naught of t is 0 because x naught, y naught is a critical point, and t naught is the point or the parameter that generated the point x naught, y naught. Now let us look at phi of t. Phi is actually a function of x and y, and x is a function of t, and y is a function of t. Therefore, by the chain rule for functions of more than one variable, we can write phi of t as the partial derivative of f with respect to x times dx over dt plus the partial derivative of f with respect to y times dy over dt. Now notice that this sum is actually a dot product. This part here is the gradient of f, and this part here is the derivative of the vector r with respect to t. In particular, applies to all parameters t, so it applies to the parameter t naught. Therefore, phi of t naught is equal to the dot product of the gradient of f at x naught, y naught. Again, since x naught, y naught is generated by t naught, dot r prime of t naught. And we have seen earlier that phi of t naught is equal to 0. Hence, this dot product is equal to 0. And when the dot product of two vectors equals 0, that means they are perpendicular. So this tells us that the gradient of f at x0, y0 is perpendicular to r prime of t0. Now, since r is the parameterization for the curve g of xy equals k, r prime at t0 is actually the tangent vector to that curve at the point x0, y0. And since this is a tangent vector, it is perpendicular to the gradient vector of g at the point x0, y0. Now we're talking about curves in the two-dimensional plane here. So if one vector is perpendicular to r prime of t0 and another vector is perpendicular to r prime of t0, then we can conclude that these two vectors are parallel. Hence, we say that the gradient of f is parallel to the gradient of g at the point x0, y0. And if two vectors are parallel, they are scalar multiples of each other. This proves the theorem of the Lagrange multiplier. So again, using the method of Lagrange multiplier to find the relative extremum of the function f, given a constraint g of xy equals k, we just find the point x0, y0 such that the gradient of f at that point x0, y0 is equal to some constant lambda times the gradient of g at the point x0, y0. The constant lambda in this theorem is called the Lagrange multiplier. Note that the theorem also holds if f and g are functions of three variables or more. We can now use the method of Lagrange multiplier to find the maximum and minimum values of a function subject to a given constraint, while assuming that these values exist by these two steps. First, we solve for the solutions of the system of equations given by partial derivative of f with respect to x equals lambda partial derivative of g with respect to x, partial derivative of f with respect to y equals lambda partial derivative of g with respect to y. These two equations came from the fact that the gradient of f equals lambda, the gradient of g. And the third equation is the constraint. Now, solving for the solutions of these systems might produce multiple solutions. So we evaluate f at all the solutions obtained in the first step, and the highest value of f will be the absolute maximum value, while the least is the absolute minimum value of f subject to the given constraint. For functions of three variables, we just have an additional equation in the system given by partial derivative of f with respect to z equals lambda partial derivative of g with respect to z. This is because f is a function of three variables, therefore the gradient has partial derivative of f with respect to the variables x, y, and z. Again, these three equations here came from the fact that the gradient of f equals lambda gradient of g. And the last equation is the constraint. Again, this system of equations might produce multiple solutions, so we evaluate f at all these solutions, and the absolute maximum value of f will be the largest of these values, and the absolute minimum of f will be the least of these values. Now it's time to solve a particular example. Let us use the method of Lagrange multiplier to find the absolute extremum values of the function f of xy equals 4x cubed plus y squared on the ellipse 2x squared plus y squared equals 1. Now, when using the Lagrange multiplier, it is very important to identify what is your objective function and what is the constraint. Recall that the objective function is the function whose maximum or minimum you want to solve. So in this case, since we want to find the absolute extremum of f of xy equals 4x cubed plus y squared, this will be our objective function. And therefore, the ellipse 2x squared plus y squared equals 1 is our constraint. So we let g of xy be 2x squared plus y squared. Following the steps that we have enumerated earlier, the first step is to form this system of equations given by the partial derivative of f with respect to x, which is 12x squared, should be equal to the partial derivative of g with respect to x, which is 4x times lambda. The second equation is the partial derivative of f with respect to y, which is 2y, should be equal to the partial derivative of g with respect to y, which is 2y times lambda. And the third equation is the constraint. Looking at equation 2, we see that 2y minus 2y lambda is equal to 0. Therefore, we can factor out 2y, and hence we have 2y times 1 minus lambda equals 0. This gives us the solution y is equal to 0, or 1 minus lambda equals 0, or lambda equals 1. So in the first case, if y is equal to 0, then substituting on the third equation, we have 2x squared is equal to 1, or x is plus minus 1 over the square root of 2. Therefore, the extrema may occur at 1 over square root of 2, 0, and negative 1 over square root of 2, 0. The second case is if lambda is equal to 1. Then from the first equation, we have 12x squared equals 4x, or 12x squared minus 4x equals 0. We can factor out 4x and have 4x times 3x minus 1 equals 0. Here we have x is 0, or x is 1/3. From the third equation, if x is 0, then y squared equals 1, or y is equal to positive or negative 1. Or, if x is 1/3, then we can solve for y to be plus minus square root of 7 over 3. Therefore, we have the critical points 0, 1, 0, negative 1, 1/3 positive square root of 7 over 3, and 1/3 negative square root of 7 over 3. So the system of equations from the method of Lagrange multipliers gave us all these 6 critical points. The next step is to evaluate our objective function f of xy equals 4x cubed plus y squared at all the critical points obtained from the previous step. Now we see that if we evaluate f at all the critical points that we obtained, the highest value is square root of 2 attained at the point 1 over square root of 2, 0. And the lowest value is negative square root of 2 attained at the point negative 1 over square root of 2, 0. Therefore, subject to the given constraint, the absolute maximum value of f is square root of 2, and its absolute minimum value is negative square root of 2. Now let's try another example, this time with a more real-life application. So find the dimensions of a rectangular box with an open top with the largest volume if the total surface area is 216 centimeters squared. To illustrate, let x, y, and z be the length, width, and height respectively of the rectangular box with an open top. We want to find the largest volume. Therefore, the function that we want to maximize is the volume of this box. Hence, our objective function is the volume of the box, given by f of xyz equals xyz. Take note that this function came from the formula for the volume of a rectangular solid. The constraint is the total surface area of this open box should be 216 square centimeters. So we solve for the total surface area of this box, which is given by xy corresponding to the area of the base plus 2xz corresponding to the area of the back and the front faces of the box, and 2yz corresponding to the area of the two sides of the box. So now that we have identified our objective function and our constraint, we can now let g of xy to be xy plus 2xz plus 2yz. Now we have this system of equations. Note that the first three equations came from the gradient of f should be equal to lambda times the gradient of g. That is, this part is the partial derivative of f with respect to x equals the partial derivative of g with respect to x. This is the partial derivative of f with respect to y equals the partial derivative of g with respect to y times lambda. And this part is the partial derivative of f with respect to z equals the partial derivative of g with respect to z times lambda. And the fourth equation is the constraint. First, note that the Lagrange multiplier lambda in this problem should be non-zero. Why? Because if your lambda is 0, looking at the first equation, this gives you yz equals 0, which means that either y or z is 0. But we're talking about dimensions of a box here, which means that any of x, y, and z cannot be 0. In fact, there should be always positive. Now we multiply equation 1 by x, equation 2 by y, and equation 3 by z so that the left-hand side are all equal to x, y, z. And hence we get these new set of equations. Now let's look at equations 5 and 6. They both have x, y, z on the left-hand side, so we can equate the right-hand side. Thus we get y plus 2z x lambda minus x plus 2z times y lambda is equal to 0. Now if you distribute x lambda over y, we get xy lambda. And then if you distribute y lambda over x, we get minus xy lambda, which should cancel out. Therefore, we have 2z x lambda minus 2z y lambda equals 0. Now we factor out 2z lambda in this case. So we have 2z lambda times x minus y equals 0. Now, since lambda is non-zero, we can have either z is equal to 0 or x minus y equals 0. This gives z equals 0 or x equals y. Again, since x, y, z are the dimensions of a box, z should be non-zero. So therefore, we take x equals y. Similar to what we did above, we consider equations 6 and 7, which has the same left-hand side. So we equate the right-hand side. That means x plus 2z times y lambda minus 2x plus 2y times z lambda equals 0. Now, if we distribute y lambda over 2z, we get positive 2yz lambda. And we distribute z lambda over 2y, we get minus 2yz lambda, which cancels out. Hence, we have xy lambda minus 2x z lambda equals 0. Again, we factor out x lambda. So we get x lambda times y minus 2z should be equal to 0. Again, since lambda is non-zero, we have x is 0 or y minus 2z equals 0, which means x equals 0 or y equals 2z. Again, x is a dimension of a box, so it cannot be 0. Therefore, we take only y equals 2z. So now we have two equations, x equals y and y equals 2z. Combining these two, we have the volume is maximized if the box with open top has dimensions x equals y equals 2z. This means that we can replace x and y by 2z in the fourth equation. So the last equation, xy plus 2xz plus 2yz equals 216 becomes, again we replace x and y by 2z. So xy becomes 4z squared. Here x becomes 2z and y becomes 2z. So therefore we have 12z squared equals 216. Or z squared equals 18, which gives us z is 3 square root of 2. Again, we take only the positive square root because z cannot be negative. Since y equals 2z, we have x is equal to y is equal to 6 square root of 2. Therefore, the box with open top with surface area 216 square centimeters and largest volume has length 6 square root of 2 centimeters with 6 square root of 2 centimeters and height 3 square root of 2 centimeters. So this ends the lecture on absolute extrema and Lagrange multipliers. I hope you learned something from this, and I leave you now with some more exercises that you can work on your own. Please don't forget to watch the discussion videos for more examples about this topic. I'll see you again.